Well, hello there, children. Welcome back to another adventure of Will He Let His Voice Last during this presentation. My name is Mr. Key, and I will be your math presenter for the next, who knows, very long time. Anyway, so today we're going to be discussing Unit 6, Day 5, Exponential Logarithmics Applications, otherwise known as fun word problems. It's so exciting, word problems, oh my god. Because of course math wouldn't be fun unless you actually had some kind of way to apply it. So, we've talked about what growth and decay equations look like. We said that this had to be what in order for it to be growth. This had to be greater than 1. Therefore, in this case, my rate, which is R, we're going to add it. Of course, we have to add the rate. 5%, 8%, 6%, whatever the rate is, we have to add the rate. Otherwise, it wouldn't be greater than 1, and otherwise we wouldn't have growth. We'd have decay. That's over here. So the rate is R. This is as a decimal. And we'll be talking about that. That's probably the trickiest part. That's the word decimal, by the way. I should probably blow this up so I can see it better. Maybe so you can see it better. All right, so I don't know why this is still here. Thought I'd get rid of that. Anyway, so we're going to talk about growth as a decimal. Let me tell you what A is. A is my initial investment or initial amount. You know, so if you're talking about money, it's the amount of money you start with. If you're talking about population growth, it's the amount of people you're starting with. Excuse me. Or the amount of rabbits you're starting with or whatever. So decay is very similar. Decay is very similar. We still have a rate, but in this case, our rate R, we're going to subtract because in order for it to be decay, it has to be less than 1. Now, I say less than 1. It also has to be greater than 0. Again, we're starting with an initial amount. Sorry, my glasses are fogging up on me for some reason. Maybe my basement's too cold. Someday I'll show you my crazy office I have here. It's awesome. Maybe you saw it the other day when my light went off. So this is the initial amount again. And we're looking for that to grow larger. Okay. Oh, and T, I forgot to tell you what T is. T is, of course, time. Now, time doesn't mean an hour, a minute, a second. It can mean anything. Riggers. So, time could be whatever, and it can be in different increments. So we're going to talk about that as well. So these are two different interest formulas. This first interest formula is a compounding interest formula, but at certain intervals. And those intervals are the n's. So in this case, n could be biannually. That'd be twice a year. Or it could be bi or semi. Somebody they call them semi-annually or biannually. They could be quarterly, which is 4 times a year. It could be monthly, which would be 12 times a year. So n is just the number of increments that we're going to be doing, the number of intervals in which we're going to be compounding our interest. Basically what happens is you start out with a certain amount. Here's how it works. You start out with let's see if I can figure this out. Let's say you start out with $1,000 and you're compounding it monthly. Well, you earn a certain amount of interest, and at the end of the month, you're earning interest on that $1,000. At the end of the month, let's say you have $1,005. Well, now you're going to earn that interest on that $1,005 for another month, and let's say you have $1,006. Oh no, $1,011. You earn $6 that time. Now you're earning interest on. So what it is you're earning interest on a larger amount every month, or every quarter, or every biannually. And the shorter you can get this increment, Usually the better it is for you, because the more you're always you're constantly earning an interest on a larger amount, right? So if I can earn 1%, if I can earn 10% on $1,000 and then 10% on $1,005, I'd rather earn 10% on $1,005 because it'll make me more money. But if I could get 10% on $1,011, that'd make me even more money. Now I know it's a little bit amount, but with that little bit amount over time is a lot of money. This formula is for compounding interest continuously. Oh, man. Anyway, what that means is it's always earning interest. You're just constantly earning interest on a larger amount, where P is the principal amount you start with. In this case, P is the principal amount we start with. Say in my case, was $1,000. In this case, R is the rate, and T is time. Sorry, kids. And in this case, N is the number of increments we're compounding. In this case, it's compounding continuously, so we use this formula with the natural base E. All right, so let's see if I can figure out how to make this make more sense for you. At the same time, not gross you out with my coughing all over everything. I don't know why I need this. There we go. So, growth. Buffalo. In the last 12 years, an initial population of 38 buffalo in the state park grew about 7% per year. Write an exponential growth model given the number N of buffalo over T years. All right. So we're going to use our growth model. Our growth model equation's right here. It's just y equals. So y equals, you could use b equals. We're starting out with 38. We're growth, and it's at 7%. Now this is the tricky part. 7% as a decimal is not 0.7. It's 0.07. So 1 plus 0.07 raised to the t. T is the time interval, in this case in years. About how many buffalo are in the park after 7 years. So this was the model. This is what they want us to create as the model, and then they want us to use 7 years. So y equals, do I have my calculator? Okay, there, I'm good. Okay, so y equals 38, 1.07. I just added them together. It makes it a little bit easier, to the 7. And that'll tell me how many buffalo I'm going to have in 7 years. So 38, parenthesis, 1.07, parenthesis, raised to the 7 years. We will have 61.01. So y equals 61.01. Now, you notice they didn't tell you where to round to, correct? That's because you got to be an idiot. So you got to be a smart guy, not an idiot. I don't know what I'm saying. So it's how many buffalo were there? I mean, clearly then our answer should be 61 buffalo. You can't have a 0.01 buffalo. Well, you can. It's called a hamburger. Now, it says, in what year were there 53 buffalo? So now we're going to do this a little bit backwards. We're going to start with 53 buffalo. We're going to use the same formula. The only thing we don't know is the time. Now, because this is your variable, right? Whenever the exponent is your variable, you know you're going to be using logs to solve it, which is why it's in this unit. So, first things first, we divide by 38. Now, I'm just going to leave this as it is because I don't really care about putting it in my calculator right now. So what I have is 1.07t equals 53 over 70. Now I want to be able to get this t by itself, right? So what I got to do is change the form. So it's all about the base. So it's going to do log of 1.07. That's the base. Now the t and this thing switch. This is not new. This is all the same stuff we've been doing. 53 over 38 equals t. And that's what we'll type into our calculator. So control log 1.0. I don't know why that does that. You tell me I don't need a computer. Control log 1.07 of 53 divided by 38 equals 4.917. So t equals 4.917. Now remember, this is years, but that's not what it asked. It asked in what year. So we got to figure out what's going on in this problem. Let's see. In the last 12 years, this probably grew from 7%. In the last 12. Oh, normally it would tell us what year we're starting in. Okay, well. So I guess our answer would be during the 4th year. Normally they'll tell you this starts at a certain year. Maybe, it might not. Weird. Anyway. No, it'll come. I'll show you a problem where it actually makes sense. What I'm talking about. All right, now we're going to do decay. So a cost of a new television is $1,200. It decreases by 21% per year. Write an exponential decay model. That means we're going to be subtracting after t years. So let's just do that part right there. That part shouldn't be too difficult. So y equals our principal amount, which was $1,200. 1 minus our rate. Now, 21% is 0.21. That one is 0.21 to the t. There's our model. Now we want to know the estimated value after 2 years. So we do y equals 1,200. Now, this is, you can put in 1.8, 1 minus 0.21 if you want, or you can just do 0.79 to the t. It doesn't matter. It'd be the same thing. So let's see what that is. 1,200, parentheses, 0.79, and they said to the second power, right? Did we say second power? Oh, we didn't want t. We wanted 2 years. We're doing 2 years. So we do 2 years. Squared. $748. So y equals $748.92. Now the question says, when will the value of the TV be $300? So we start with $300, and this is the one where we're going to have to use logs. When they just ask you to type in for t or plug in for t, that's easy. But when they when the problem requires us to find the number of years, in this case t, we're going to have to use logs. So the first thing we're going to do is divide by 1,200. So one thing you guys should get good at is casting out zeros. Gone, gone, gone. This is just 1/4. So I get 1/4, or 0.25, is equal to 0.79 to the t. Now, that's probably right where my head is. So if you didn't see that, and I forgot to move my head on the screen, I apologize, but there it is. We started with 300 equals 1,200 times 0.79 to the t. We divide by 1,200. So in order to do this, we got to change its form. So we're going to do log. It's all about the base, 0.79. And then these two things switch. Of 1/4 equals t. So we come over to our calculator. We do the log of 0.79 of 1/4 is just 0.25 equals 5.88 years. So t equals 5.88 years. So the question says, write when will the value of the television be $300? After 5.88 years. I'm going to come to a better question soon. So compounding interest, you deposit $2,900 in an account that pays 3.5% annual interest. Find the balance after 1 year if the interest is compounded monthly and annually. So we're going to do two. So we've got two different problems to do here. We're going to do monthly over here and annually over here. Okay, so formula. Go back, right? Interest. Start with the principal amount. 1 plus the rate over the number of months raised to the number of months times t. So let's see what we got here. Y equals, start with our principal amount. We're going to start with $2,900. Nothing's different right now. Y equals 2,900. 1 plus 1 plus. Now, here's what the difference is. Now, the rate's the same, so we're going to do the same rate. Now, 3.5%, be careful with that. 3% would be 0.03. So 3.5% is 0.305. You got to be careful of that. That's the hard part, I think, about most of this stuff, is just getting that interest rate right. So in this case, it's monthly, so that's 12 times a year. In this case, it's annually, so that's 1 time a year. So this is going to be 12 times, in this case, 1, because my time is 1 year. And this is 1 times 1. All right, let's see what we got here. It's 1 because it's the number of times we're doing it a year, and it's 1 here because it's the number of years. Hopefully you can see that. It's above my head. All right, let's grab our calculator. Where is my calculator? Okay. So I'm going to do 2,900, parentheses, 1 plus, I'll do control division just because you can see it, 0.035 over 12. So you'd think, yeah, you're not doing as much because you're dividing by a number, but then we got 12 times 1. I'm just going to put 12 times 1 in. And you get $3,003.14. So Y would be equal to $3,003.14. So do we expect it to be more or less over here? If you understood what I talked about earlier, you'll know the answer to this one. Now, we're going to do this exact same formula. The only difference is we're only going to compound it once, but we're only going to have to divide by once too. And we hit enter. $3,001.05. $3,001.50. Sorry, and 50 cents. So it doesn't look like it's a big difference, $1.50, $1.64, whatever it is. So why bother? Well, let's see. Remember, it's over time. So let's say this was over not 1 year, but 10 years. This one would have $4,090, and we'll go up to this one up here. And instead of 1 year, we do 10 years. So 4,090 versus $4,113.20 basically. So the difference here now would be $23. Remember, it's over time, right? So we're talking about more about time. Let's say it was over 30 years, because when you start investing money, what you want to start doing is start investing over quite a long time. So in this case, let's invest it over 30 years. I'd have $8,274 if I compounded monthly. And the only thing I'm doing is adding the interest on every month rather than at the end of the year. Now I've got, I don't know what the difference is there. $140. $140 difference. You're like, who cares? 30 years, $140, who cares? Okay. So now let's say you've got money. And you don't just have $2,900. Let's say you have $50,000. Oh, I put 5,000. I meant 50. I think it'll be more. $50,000. You'd have $140,399. So you started with $50,000, you'd have $140,339 if you compounded only annually. Now let's see what it would look like if we compound. I'm just going to do this one monthly. So now we're going to compound monthly. Now we're talking about $2,500. And all we did was change when we compound the interest. You can only imagine if you had even more money what that would do. All right, you deposit $5,000 in an account that pays 3.72% annual interest. Find the balance after 3 years if it is compounded quarterly. Now, quarterly means times 4 times a year. So we're going to start with y equals our initial investment of $5,000, 1 plus, now our rate is 0.372, so we're going to go 0.0372. Remember, if it was 3%, it would just be 0.03. Quarterly is 4 times a year, so we go 4 times after 3 years. So in this case, 4 times 3. We'll grab our calculator. We'll start with $5,000. Parentheses, 1 plus control division 0.0372 over 4 raised to the 4 times 3. And that's $5,587. So y equals $5,587 and 45 cents. Oh. All right. The residents in the United States 2006 was 298 million people. Ooh, this interest rate's going to be difficult to deal with. Be careful with these kinds of interest rates. We'll talk about that in a second. Let's see what else we got. Rate grows continues on the model using. Let me pause this because my formula is gone. Oh, sorry, man. I was kind of vegged out there for a second. I don't know what I was thinking. All right, I'll need a function. We got to create the function. So what we're going to do is going to create the function called P of T. P of T is going to be a growth model where we're just growing at 9% per year. Not compounding at all, it's just growing at a certain amount. So we're going to start with our initial amount, which is 298 million. Now we're going to use just 298, not 000, 000, 000, 000, 000. That'd be kind of silly, right? So we're going to grow at 9% per year. So 1 plus, I'm going to come back to that interest rate that we're going to add there, to the T, right? To the number of years. So 9%. Let's go 10%. 10% is 0.10. 9% is 0.09. 8% would be, well, let me do 1%. 1% would be 1% would be 0.01. So 0.9% is less than this. So I want 0.9%. Then put that point in the right place. 0.9%. So that's equal to 0.009. So that's what I'm going to add here. 0.009. All right. So when will the population of the United States be 310 million? So what we want to do is figure out when will it be 310 million. So we're going to convert this. It's all about the base. So log 1.009 of 310. Oh, man, I forgot to isolate the weird thing. Are you all like yelling at me? Mr. Krause, you didn't isolate the weird thing. Got to get the weird thing alone before you start changing base. Divide by 298. So now that I've got this weird thing all by itself, I'm going to change the base. So log of 1.009. Now these two things switch. Of this fraction, 310 over 298. And again, there's no reason to like get an intermediate decimal value. That's just going to give you problems. Is equal to t. And that's what I'm going to type into my calculator. So control log 1.009 of 298 divided by 310. And I get, I knew I did that wrong because I knew that was going to be a negative number. Let's try that again. 310 divided by 298. 298. This is bigger than 1, so it'll be positive. 4.406. So t equals 4.406. Oh, could use a rest, kids. 4.406. All right, so this is years, right? So a little over 4 years. Now we got to go back and says, because the question says, according to the model, when will the population of the United States reach 310 million? Well, this started since 2006, right? So if I take 2006 and I add 4.4 years, it's going to be 2010. So during 2010, it will be 310 million. According to the model, when will this population reach 360 million? So we're going to do the same exact thing. So now that we've done all this work, we really don't have to switch and change and do all that craziness. It's the same exact thing. It's still going to end up being log of 1.009. But in this case, instead of 310 on top, we're going to use 360 over 298 is equal to t. All right, so now we just do the same exact thing. All I got to do is change this to a 60. And now I'm going to add 21.1 years. So t equals 21.1 years. So we'll take 2006, and we'll add 21.1 years, and that puts us in 2027. So during 2027, our population will reach 360 million. Sorry. So we're going to do the same kind of thing. We want to create the model P of t for population. So P of t is equal to, what are we starting with? This is world population, I'm assuming, right? Population of the world. So 6.53 billion people, growing at a rate of 1.4% per year. So we're going to go 1 plus 0.0114. 1.14%, 0.0114 to the t. That's our model. So what I mean by model is that's our equation that we'll use to solve these things. So according to this model, when will the population reach 9.25 billion? That's when the earth just falls apart. So 9.25 million. If we would continue on this growth, when will we be there? 6.53, 1.0114 to the t. Isolate the weird thing, so we'll get that weird thing all by itself. So this goes and this goes. And what we do now is we're going to change the form. So we'll go log, it's all about the base, 1.0114. And then those two things have to switch. So this thing, 9.25 over 6.53, and that's equal to t. So control log 1.0114 of 9, forgot the numbers already, 925 divided by 6.53. 6.53. 30.7 years. So t equals 30.7 years. Let's see. This was 2006. So if we take 2006 and we add 30.7 years, that's 2036. Now you don't want to round because it says in which year? According to the model, when will the population? So your answer's got to be something like during the year 2036, the world population will reach 9.25 billion people. Something like that. According to this model, when will the population reach 11.7? All right, if we ever get to 11.75 billion, holy mackerel, always standing next to each other. So 1.0114. There won't be enough water on the earth for this. 11.75 divided by 6.53. So it's the same model. The only thing I'm changing now, the only thing I'm going to change is what population I want to end up with. And that's going to give me another year for t. So I'll just redo this one. And instead of this, I'll change this to an 11.25. So 47.987. So t equals 47.987 years. Oh, wait, it's 7.5. I put 2.5. Shoot, sorry, kids. Got to change that. It's just to talk to you about rounding, but I'm not going to have to because this is going to change it pretty good. Back 7, enter. 51.8 years. Well, I'll still have to talk to you about rounding. So 51.8 years. So we'll take 2006. We'll add 51.8. And you get 2057.8. So during the year 2057, we will have 11.75 billion people on the earth and no water. So we got to curb our growth somehow, kids. All right, the Chevy Cobalt. I don't even think they make a Chevy Cobalt. Let's call this the Chevy Cruze because now we have a Chevy Cruze. Can be modeled using this equation. Now, I want you to ask me, is this growth or decay? Right? That number is between 0 and 1, right? So therefore, it's decay, and of course it's decay. It's a car that's dying. So and if I asked you what was the starting value of this car, you'd say it was a $14,512 car. So I want to know when will it equal 9,000. Well, so what we're going to do is we're going to say 9,000 equals 14,512.82 to the t. Now, notice I'm going to ask the same question each time. So once I do this math, I don't have to actually go through and do that same math again. I just have to change numbers. First part of the math is isolate the weird thing. Get the weird thing alone. So we're going to divide by $14,512. Those go. Those go. Now we're going to change the form. It's all about the base. So log base 0.82 of 9,000 over 14,500. 14,512 is equal to t. So, come with my calculator. I'm going to do control log 0.82 of 9,000 divided by $14,512. 2.4 years. So t equals 2.4 years. So what's the question asked? According to the model, when will a car be worth $9,000? In 2.4 years. It didn't say it around, but I would say in 2.4 years. So we're going to do the same exact thing, but now all I got to do, I don't have to do all the work. I just got to change this, and now I want to know when it's going to be worth $4,000. And that's in 6.49 years. So same work, log 0.82, but in this case it's 4,000 over 14,512. And we would say equals t. And we would say in 6.49 years. 6.49 years. Normally, if they don't ask you to round, first of all, they're stupid, but you don't round. You just give the whole thing out there. But that would be kind of dumb in years. Nobody cares about 0.49834 down to what, minute and second. Especially with some of our drivers. Might be worth that in like a day, the way some of you drive. Oh, I've seen some of you driving. It's not pretty. 14,512. So we're going to do the same exact model, but this time I want to know when it's equal to 2,000. So it's chink, chink, chink. Now this is all relative, of course. You know, this is just based on history, 9.98 years. So t equals 9.98 years, which is pretty much 10 years. Just about 10 years from now. All right. So again, we got another depreciating vehicle. In this case, it's the Dodge Stratus. Again, a vehicle that does not exist. So we'll call this the Dodge Ram. Of course, there's no Dodge Ram that is worth $19,282 to begin with. But we are depreciating in value. Now, which one depreciates faster, 0.84 or 0.82? So in this case, the 0.84 will hold its value a little bit longer. This is only worth 80%, 82% of what it used to be the year before. Now this one is worth 84% of what it used to be. So that'll tell you which one depreciates faster. And we're going to do the same exact math here that we just did. We'll start out with our model. We got to create a model, although I gave you the model. So we're going to just do 15,000 is equal to $19,282, 0.84 to the t. Now we're going to just create this model, do it once. Oops. Divide by 19,282. Divide by $19,282. So I get t. Oh, why am I doing this? Let me go change colors. Maybe my brain will function better. These go. So now I'm going to change the base here. So log of 0.84. Now, of this thing, 15,000 over 19,282 is equal to t. So that's what I type in my calculator. Control log 0.84 19, nope. 15,000. Control log 0.84 15,000 divided by 19,282. Enter. 1.44 years. So in this case, t equals 1.44 years, approximately. It doesn't say the year. It just bothers me. See, like if I was the year is 2008, and then you'd have to say, okay, in 1.44 years, you'd say that's 2009. So halfway through, just about halfway through 2009, it would be worth $15,000. Now we're going to do the same math, but now I don't have to redo all this math. It's log 0.84 of 8,000 divided by 19,282. Now my math over here is just to change the 15,000 to now 8,000. And we get 5.045 years equals t. So t equals 5.045 years. That's years, by the way. And we'll do it one last time. When's it going to be worth 2,000? After t equals 12.99 years. So basically 13 years from now, it will be worth $2,000. The average cost of a college, if the college increases by 5.5% interest, what would the average cost of a college at 4-year private college be in 2015? This is 2005. So first we got to create the thing. So cost over time. I could just use Y there if I wanted to. We started at $29,026. It's increasing, so we're going to add 5.5% per year. So it's 0.055 to the T. Well, they want to know what will the cost be in 2015. Well, if you notice, that's 2005 to 2015. That's 10 years into the future. 10 years into the future. So my cost of basically 10 in 10 years will be 29,226. 1.055 to the 10. Let's see what it's going to cost in 10 years. So 29,026 parenthesis 1.055. I think I got too many fives in there. Raised to the 10. 49,580. So cost in 10 years will be $49,580. And 60 cents. Don't forget that 60 cents. That won't buy you anything. All right. A college plan, this is my last problem. A college plan such as a 529 plan allows individuals to put money aside to help pay for college. If 1 plus plan, 4% compounded continuously. So I knew I was going to do one example of compounding continuously. That's the y equals PERT. Y equals principal e to the RT formula. So how much should be put into a college saving plan in 2005 to pay for 1 year of college, the cost of college at a 4-year college in 2015? So we're going to use what we just figured out. We just figured out that for 1 year of college, it's going to cost $49,580.60. So that's our Y, $49,580.60 is equal to, we don't know what we're going to start out with. Got to kind of figure that out. How much should be put in 2005? E, R is 4%, so it's 0.04, and we have 10 years to pay for it, so 10. Okay. Well, remember, this is just a constant. So we just got to figure out what that's equal to. So it's 49,000. So all we're going to do is divide by that. E 0.04 times 10. Go to our calculator. We'll take this number, enter, and we're going to divide it by, that's a bad way to do it. Control division, $49,580.60. Forgot the 4 That would make it sort of, my goodness, control division. $49,580.60 all over e to the 0.04 times 10. You could have just done 0.4 there, but whatever. And you get $33,234. So P, your principal amount that you should invest now, is $33,234.87. So if I was telling you, I'd say P equals $33,235. I wouldn't care about the cents because I don't think they care. Anyway, that's an example of PERT, I guess. That's it. That's all she wrote, kids. That is exponential growth in word problems. I hope you had fun. Hit the subscribe button, hit the like button, or you can comment.